Howdy, and welcome to the Lost Rider podcast. It's an honor and a privilege to address you in the capacity of an interviewer, reporter, and media member. Too many modern media outlets have forgone the integrity and responsibility required of credible information sources. What you will receive here are straightforward discussions with legislators, agency leaders, biologists, engineers, doctors, and countless other experts that have the answers to questions often circulated as kitchen table issues. The title Lost Rider may be thought of literally as well as in the metaphorical sense. While there has been the instance that I was momentarily a little turned around at night in a wilderness area, the idea of being a lost rider in life, well, that fits most folks at some time. These renderings are coming to you in the form of the 25-year-old radio program, The News from the Camp House. It still airs every Saturday morning at 6:30 a.m. Central Time on KULM 98.3 FM out of Columbus, Texas. The original intent was to relate outdoor topics to the general public. Immediately, it was found that all issues are relatable to the outdoors and that people are people. They all play a role and they all have a vested interest. It's this program's desire to answer common questions about how the world works, how it will operate in the future, and what's the holdup? So please listen, enjoy, and never hesitate to contact us with more questions and feedback. Good morning and welcome to this weekend's edition of News from the Camp House, listening post of the Texas Sportsman Association. This is Herman Brune. This weekend's edition is also brought to us by Shaw's Bend Country Club for folks who don't have a country club. All right, we've got a special guest with us this week. Gentleman who has not been with us before. He's going to try to give us some information, see if we can absorb it. This is some stuff that we've been hearing a little bit about. We don't know hardly anything about it. It's Mr. Chris Hall. He is with a group called ITER. It's a project that they're working on. He is actually works from France. This morning, he is talking to us from Milan, Italy. He was in Germany. He's going home now to France. They're sending him home through Italy, and he's taking time to stop and talk with us this morning. Mr. Hall, thank you for being with us this morning.
My pleasure, Herman. Thanks.
Okay. All right. Now, the subject matter is fusion. People over here, and I don't know, I would expect it's that way everywhere, barely are trying to scratch the surface on accepting nuclear power. Fusion is something that, we've heard about since I think I was little. But it was always something that was futuristic, that was like science fiction. Would you please explain as simply as you can about how fusion works, that people would make energy out of fusion?
Sure. Okay, no problem. So fusion, nuclear fusion, that's what we're talking about. Nuclear fusion is the power source that drives the sun, our sun, and every star. Fundamentally, I often call it the universal power source, because in reality, the entire universe is powered by fusion, by nuclear fusion of hydrogen ions. So most of the universe is made from the most simplest atom, hydrogen. Just a hydrogen atom. What is it? You've got in the middle a proton, a pretty fundamental particle, and then supposedly in the beginning of time there were only the protons, and then the universe started to cool, and these protons started to form into hydrogen, which is a proton and an electron, the simplest atom. So on an atomic level, you've just got a simple proton, which is positively charged, and an electron orbiting around it, which is negatively charged. And those balance to become the molecule, hydrogen atom. And so hydrogen is the most basic thing. It's much of the mass in the universe, the known mass in the universe, visible mass. And if you squeeze it together enough, so if it's attracted by itself by gravity, which is how we understand that stars were formed. These protons slowly cooled after the Big Bang. They formed into hydrogen gas. And then these molecules of gas are slowly get drawn to each other through the process of gravity. And they get larger and larger. And as they get larger, the gravity that they create is becoming stronger and stronger. And they're starting to squeeze and push themselves into a greater and greater, bigger and bigger ball with higher and higher density and therefore temperature in the middle. And over time, that density and temperature build until the atoms are squeezed so tight to each other that they overcome their inherent resistance to each other. They have a repulsion from each other, which is why you can't walk through a solid object. You and I is because of this electrostatic repulsion that's at the core of every atom. But if you push those things together strong enough, eventually you'll cause fusion. So you'll get the atomic nuclei. In this case, in hydrogen, it's just a proton. You'll get those protons to stick together and become something different. So what happens is these two protons are forced together and they actually break down and there's a very complicated rearrangement of all different kinds of nuclear reactions. But fundamentally, these hydrogen atoms become helium atoms. So there's a nuclear reaction. Hydrogen becomes helium. So instead of having now just one proton in the center, now you've got two protons in the center, which were previously separate atoms from hydrogen. So that's the reaction, the nuclear reaction fundamentally. And actually, all matter is formed in this way. And you can continue fusing things together. You can fuse helium together. So you take your two and you squeeze another helium together and you can come up with a thing with 4 in the middle. You can squeeze that, a 4 and a 4 to make an 8, an 8 and an 8 to make a 16, and such the atoms get bigger and bigger and bigger until you reach iron. Iron is like, for some complicated atomic reasons in the center, iron is the biggest molecule that you can form in a sun, in a fusion reaction. And beyond that, everything big, all the atoms larger than iron are formed in different processes, typically supernovae explosions or other atomic complicated impacts where high energy particles are absorbed by atomic nuclei. But okay, we won't go too much into atomic physics, but fundamentally fusion is sticking small molecules together to form bigger molecules. And okay, so what happens is that when they stick together, if we say we've got one unit of mass of hydrogen and another unit of mass of hydrogen, when they form together to make helium, the helium doesn't weigh 2. We have a slight loss of mass. It's minuscule. It's absolutely minuscule. On a single atomic level, it's almost unmeasurable. But that mass is directly converted into energy. So you'll have heard of the equation, Einstein's famous equation, E equals mc squared. So energy is equal to mass, m, times c squared. And what is c? C is the speed of light and squared. So the speed of light is a very large number. If you square a very large number, you get an even bigger number. So 3 times 10 to the 8 squared Okay, 9 times 10 to the 16. So you now got a 9 with 16 zeros. So you can see if you multiply that very, very large number by even the tiniest amount of mass, you get a huge amount of energy. And fusion is an extremely energetic reaction. So the fusion of two hydrogen ions generates more than 3 times the energy of the fission of a big uranium atom that we use. So as we know that uranium fission, or nuclear fission, as what is typical in nuclear power plants today, that's also an extremely energetic reaction, hundreds of times more, thousands potentially more powerful than a combustion reaction. But then fusion is even more powerful per unit reaction than fission. And that's why the sun and all stars are extraordinary. They generate massive amounts of power. They heat the universe. They send out energy throughout the universe. And that's why I often say that fusion is the universal power source, because in fact, almost all the energy certainly all the energy that we receive on Earth is from our sun. And that's just by being relatively close to one star. And that star is obviously generating energy in all directions, but we're just getting a little bit. But the quantity of energy being released at every moment is so large that is enough to keep our planet warm and drive all the processes that we see on it.
All right, let me inject something right quick. This is my listeners. We start talking about atomic stuff, and we're pretty quick, run right past everybody. But no, when you start speaking about hydrogen, of course, now there's people who have been paying attention are going to realize that, yes, we've heard about using hydrogen as a form of energy. People are barely accepting the idea of nuclear micro reactors. We're hearing more about that. I expect as we hear more about it, people will become more accepting of it. We get more news about it. And of course now fusion, they did a very good job of explaining that. I don't know how good of a job we're going to do understanding it, but yes, one of the reasons that this has become relevant is because of science marches forward. We're looking at all the AI stuff. We're looking at all the desalination stuff, everything that's coming up on our radar here in the near future. It's going to require great amounts of energy. And these words are starting to come up. The future is here. The words that we've been hearing for so many years, the future is here. And we just need to start hearing these things and understanding that they're going to be here. The AI, the data centers, the word on the street is that they're going to be allowed to make their own electrical sources that they can't pull off the public power grid. They're going to make their own electric sources. And eventually this is the desal plants, the largest seawater desal plant in the United States is being built in Port Aransas, Texas, on Harbor Island. They are going to be needing large sources of energy. And so that's why we're talking about this stuff. That's why we want people to get used to hearing about it and have some relative idea of how this is going to affect people and how it's going to work. And, get used to it. This isn't science fiction. I'll tell you what, let's take a quick break. And thank you folks who let us come on here every Saturday morning. We'll be right back. Thank goodness for all the great sponsors we have here at News from Camp House. H-E-B Food Stores. That's Stephen Tice at H-E-B. He helps me. He helps the community. He's a great man. I'm so thankful H-E-B loosened him up, lets him go around and sponsor a few things. H-E-B's got all your food needs. It's the greatest food store we got here in Columbus. Thank goodness for H-E-B. First State Bank. You go over to First State Bank, they'll take care of all your loans, all your deposits, your savings, anything you need. Bunch of great hometown people over there. You got Celia Tobias, John Pollock. Everybody over there is looking out for you. Miss Barbara Barta. It's a great bunch of folks at the First State Bank is also sponsoring News from the Camp House. First State Bank takes care of all my business. Baumgart Agency, Susan Baumgart at the Baumgart Agencies, her and Germania. She told me to plug Germania. Germania is an insurance that she likes to everybody to know about. The Baumgart Agencies. Miss Susan and I are classmates, being classmates. She got me out of high school, sat right beside her, put us in alphabetical order where I could copy. And Susan Baumgart over at the Baumgart Agency taking care of all your insurance needs. Lyco Realty, one of the original sponsors of News from the Camp House. Lyco Realty, the oldest real estate company in the county, and for the last 3 years voted the favorite realtor in the county. Lyco Realty, that's Miss Kimberly Johnson, that's Crockett's granddaughter. More kinfolks and classmates and great people from Colorado County. People from Colorado County helping people from Colorado County. That's great. Oh, thank goodness for all these wonderful people come to me want to be sponsors for News from the Camp House. Good morning and welcome to the second half of this week's News from the Camp House Listening Post Tech Sportsman Association. This is Herman Brune. We're here with a gentleman this morning. This morning's recording is coming from Milan, Italy. It's actually Mr. Chris Hall is with us. He is. Tell me a little bit about ITER. This is a project that you are working on, Major International Fusion Energy Experiment, is the way it was explained to me. It's called ITER, and if this works, if this is something that, is cost effective and safe, and if this works, this is going to be a major new energy source for everybody. This is an international project. So go ahead.
Yeah. So as I explained before, the science of fusion, and like you say, humans are always looking for new sources of energy, and there's particularly electricity use is growing, and we move away from other sources of electricity such as coal and gas and carbon emitting sources. There's always a need for new things. So why don't we have fusion already? If it's powering every star, let's have it on Earth. But it's difficult to do. That's the reality. It's extremely difficult to do. What stars have that we don't have here on Earth is mass, incredible mass. So they have a gravitational force that is beyond what we could ever generate, at least certainly at this time on Earth, without fundamentally changing our understanding of gravity. So the stars squeeze the atoms together and until they fuse together. We simply couldn't generate that kind of pressure on Earth through any feasible method. So what we have to do on Earth to make fusion happen, and fusion reactions have been happening since shortly after the Second World War in the 1950s. What we have to do is we have to accelerate these atoms to extremely high velocities, high energies, and then we smash them into each other. And if we can get them to high enough speeds and then hold them together for long enough time, there'll be sufficient collisions that are just right that these things will then overcome the repulsive force that normally just they deflect from each other, they bounce off each other. But if we can hold them for long enough at high enough temperature, they'll actually start to fuse. And this has been done in many different reactors around the world, as I said, for 70 years now, with increasing capability. And every time as a breakthrough, famously in the UK back in the late 50s, they had really thought, well, some people thought that they had solved it. We've done it. We've made neutrons, which is an indication of fusion. We've made the fusion reactors, problem solved. But they had only just discovered the next challenge, actually, and then which took a long time to overcome. And then as they got closer to that, maybe sometimes in the 60s, they discovered new challenges. You have to, in order to create, when you bring these atoms up to the kinds of temperatures we're talking about. So at ITER, we want to make we want to heat the hydrogen to about 200 million degrees Celsius. Kind of a crazy number. Okay, 200 million degrees Celsius. You need above 150 million degrees Celsius before the atoms are going sufficiently fast that they will fuse with each other. So that we're not talking about a solid or a liquid or a gas. We're talking about plasma. What plasma is the next phase of matter. So if you take ice, you heat it up, it becomes a liquid. If you keep heating that water up, that liquid ice, it will become steam, it will become a gas. If you keep heating that gas, eventually what will happen is within the molecules, within the molecules of water, they'll start to dissociate and become a plasma. So that's where actually the what we call the ion, which is the central part of the atom, becomes free from the outer part, these electrons. So at the very beginning, I talked about in hydrogen gas, you've just simply got the proton and the electron spinning around it. But if we heat that gas hot enough, the electron comes off and goes free, and you get a soup of positively charged ions, which is the big part of the proton, essentially. And then you get these free electrons that are swimming around. And this is called a plasma. A plasma is magnetic, it's electrically charged, it's a different thing, it's a different phase of matter. And actually, most of the universe is plasma. The sun is a big ball of plasma. Clouds, nebulae, or big balls of plasma. And there's not a lot of plasma on Earth. Lightning is an example. Fire is an example of plasma. But most on Earth were relatively cold, relatively low pressure, and so you have solids and liquids and gases. But okay, so we generate this plasma in these reactors where we're trying to heat this plasma up to incredibly high temperatures and create fusion. The trouble is, it's extremely difficult to maintain something at this kind of temperature. It's extremely difficult because our world is cold. So these reactors that we put these things in are cold. If the plasma touches the surface of the reactor, it's not that with the reactor breaks, it's that the plasma goes cold and it stops. It becomes a gas, and the reaction stops. And the big challenge has been for 70 years making a stable plasma with enough energy to make these reactions happen. And that has been a whole new field of physics. And since this work began, plasma physics. How do you contain a plasma? How do you get energy into a plasma long enough that we can start to get these reactions inside the plasma? And there are many, many reactors around the world. There's a big one in San Diego. There's a big one in Princeton Lab. Those are the two big American devices. And they've had very good success at making very powerful fusion plasmas that have produced energy. But every single one on the planet until this moment has consumed more energy to do this than it's produced. And the best we ever got was a reactor in the UK, where called the jet reactor, and they produced about 2/3 of the energy that they put in. So they got 2/3 back out of what they put in, for a period of about 1 second. So that's the best. A similar thing, and maybe some of your listeners will be familiar with, a facility in Livermore Lab in California. They have called the National Ignition Facility. They are using a different process with lasers to try and squeeze a solid target so tight that it will actually also fuse. And they've had some success too, and they've actually, for a fraction of a second, also generated, in fact, they're the only people ever to have generated more energy than they put in. But it's kind of a cheat because it's done with very large lasers, which themselves have a huge amount of energy cost. And so really they were only counting the energy released by the laser itself, not the energy to make the laser. But so on Earth, as yet, we've not managed to create a sustained fusion reaction which generates more power that we put in. And what we're trying to do at ITER, this is the next reactor, and its fundamental goal is to generate more power than we put in and sustain that for up to, longer term, up to 1 hour. So we've got a number of different goals. The first goal is to generate 10 times as much energy as we put in. So this is something we call the Q factor. How many more times do you get out than in? And as I said, at the moment, all reactors have got a Q of less than 1. For a brief moment, Livermore produced a Q of greater than 1. But what we want to do at ITER is produce a Q of 10 for up to many, many minutes and up to an hour eventually, to demonstrate that a sustainable fusion reactor is feasible. So ITER will never generate power. It's an experimental reactor. It's just to prove that we can harness this source of energy, that we can make sustainable fusion on Earth. And I often make the analogy between fire. In the pre-fire age, humans were running around. We saw fire here and there, but we probably started playing with flints and could make sparks. That's kind of the stage we're at now with plasma. It's a different kind of fire. It's like a nuclear fire. And we can make sparks, we can make these fusion reactions momentarily, but we've never been able to light and sustain a fire. And what we're trying to do at ITER is trying to exactly that, to ignite a plasma and keep it burning, keep it sustained, keep it steady, without it going unstable, touching the wall and cooling and ultimately quenching, stopping. So now we're doing that by increasing the scale of the reactor. This is the biggest fusion reactor ever built. It's 10 times bigger than the biggest existing. And it's a huge investment, huge complexity, a lot of novel technology. And the genius of the project actually was back in the 80s, Ronald Reagan had a meeting with Gorbachev, and they were looking for a new area to collaborate on. So as the Cold War was warming up, let's say, as things were the tensions between the two countries were fading. And some smart guy in the background said to Reagan, we should look at fusion because this is something that is not really a weaponizable technology, something that is very, very difficult. Funding is needed from both sides, technology is needed on both sides, and Russia was actually in many ways really advancing in some good ways with it. So they decided to come together and make an international project, a joint project, to jointly make a reactor that could prove fusion. That was in the 80s. Here we are, some 40 years later, and we're almost built this thing. So we are about 8 or 9 years away from finally realizing this reactor. In 2035, it will be built, and we'll start to make some serious plasmas, and over the course of the following 4 or 5 years, so our current schedule is by 2039, we will make this nuclear plasma with this energy generation of 10 times. That's our target. And I think at that moment, we kind of changed the world, because we prove it goes from being a kind of an interesting laboratory experiment. Oh, look, you can do this thing. If you put enough energy in, you can make a new reaction, to actually becoming a harnessable power source. We can sustain this nuclear reaction, generate power from it. And suddenly it's no longer an idea. If this is something that can happen, it becomes like it's the new industrial revolution. Oh, well, now we can make fire. Let's start to harness it and make boilers and make steam and make energy from it. And all the secondary side, the energy generation side, is the same. We ultimately create something that is hot, capture that heat, boil water, make steam, turn the turbines, generate electricity. So all of that side of stuff is traditional. What we're trying to do is just make a new heat source, and I'm optimistic. I believe it can happen. I think technology has moved on. We've seen so many barriers. have been found and then overcome, and the physicists are extremely confident that with the ITER machine we will be able to go cured with 10. Now, it's been said before, so it's possible, certainly possible, that we have to be realistic that we find a new physics. But I think this demonstration in Livermore recently, where they did create more energy for just a fraction of a second, proves that it is possible. The sun shines every day. It proves it's possible. So we just have to find a way of sustaining it on Earth.
All right. Okay. No, that's great. I'm sorry, man. We could sit here and talk about this all day. This is great stuff. And, I want my listeners to realize, because they're going to hear more about fusion. I've already started hearing more about it, just going to, various meetings and stuff. And you've got some of your engineers, some of your executive directors, different agencies, and they're talking about the coming of nuclear power, the coming of fusion. So I'm sorry we're out of time, Chris, because we can keep going. I think my listeners are picking up a whole lot of information right here, and I hope this satisfies me. And when you get back to France, we're going to have to try to do this again. So, folks, I hope thanks for being with us this morning.
It's a pleasure. If I just have one final word, which is that I invite your listeners to go to the ITER website, which is really a very, very informative website about the ITER project and the wider fusion industry. That's ITER, iter.org.
Okay, that's iter.org. You can go find out more about this. All right, Chris, thanks for being with us this morning. Now,
thanks very much.
Everybody go out, have a big weekend, be safe. Realize you've learned a lot this morning. You've just got a lot of information. You can go out and talk smart. Be safe. Have a good weekend. Everybody go have a lot of fun. And y'all just remember, pretty much any day is a good day to be out in the woods.